So I see a lot of familiar names. I'm assuming most know who I am, but for those who heard about this or were referred to us and don't know me, I'm Sam Charrington. I am the founder of TWIML and host of the TWIML AI podcast. I wanted to share, before introducing Robert, just kind of a quick word on, what TWIML is about broadly. I see our mission as sharing and amplifying the voices of a broad and diverse spectrum of ML and AI researchers, practitioners, and innovators. And in doing so, helping to make machine learning and AI more accessible and enrich the lives of you, the podcast listener community, and broader TWIML community, and your communities. And in that vein, I've been thinking a lot about, our role and particularly our role with regard to education. We started doing these study groups. I should have looked this up. I want to say a couple of years ago. I think it really took off when, in an interview with Rachel Thomas of Fast AI, I admitted that I've been wanting to do the course for a long time and had been putting it off, but finally was going to do it, made that commitment on the air, so to speak, and invited anyone who wanted to join me to participate. And a lot of people wanted to take that course. And the community now that's kind of grew out of that is over 3,000 people strong. The Slack channel is, very active and engaging and supportive. And we've helped, I think, I haven't done a formal count, but hundreds of people kind of complete multiple fast.ai courses now. We've got a great community of volunteers that have sprung out of that and have participated in, either leading study groups or, leading meetup presentations. It's really been a fantastic community to be a part of and to watch and to support. And so, what we're talking about here is Robert. So kind of with that all in mind, one of the things that's been on my mind recently and is high on my list to do more of in 2020 is to kind of lean into, our role as an educational force, so to speak. And I mentioned that I met Robert at NeurIPS and we started talking, and he told me about this course that he was doing, or sequence of courses. And we started talking about collaborations and, what you're about to hear from him, and generally the idea of us collaborating together to bring this course to our community is, one of the fruits of that kind of leaning into education. And, I hope to bring, many more concepts to our community, including the course we're doing with IBM, the AI Enterprise Workflow course that you'll hear more about later this month. And so this is a great opportunity for us. It's the first time we've had kind of a first-party instructor participating and delivering a study group with the community. So I'm going to now turn the reins over to Robert to tell us about the course and we'll talk about causality in general, broadly, and share some of the details about the course, and then we'll kind of open it up for a Q&A. But I'll be kind of moderating the questions. So as you come up with them, just put them in the chat. With that, I'm going to pass the baton over to Robert.
Hi, everybody. My name is Robert. I'm really happy to be on the call.
Quick, before you get too deep in, someone is requesting that you go louder. Maybe in your mic settings, you can turn that up or something, or get closer to the mic.
How is this? Is this better?
Oh, wow, that's loud. Better. Yeah. Great. So thumbs up, much better, folks are saying.
All right, so a bit of okay, so just a little bit of background on myself. My name is Robert. I'm a research engineer working in machine learning. I have done a bunch of research during my PhD and post-PhD on causal modeling and causal inference. And I run a series of online workshops and a newsletter related to topics in machine learning, including causal modeling. So since we're already a bit behind schedule, I'm just going to dive in. Right here. You can see my screen okay?
Yes.
Great. All right, so as Sam explained, we're seeing this resurgence of, or I guess emergence of elsewhere for a while, but we're now kind of coming to grips with the fact that we need causal reasoning to bring to bear on machine learning problems. So just looking at a little bit at popular science here, we have a book by Judea Pearl, when he, towards the end of the book, he explains that when my house robot turns on the vacuum cleaner while I'm asleep, I tell it, you shouldn't have woken me up. I want it to understand that vacuuming was at fault, but I don't want it to interpret the complaint as an instruction never to vacuum upstairs again. So he goes on to explain that this means that we need machines that recognize intent, and argues that intent itself is a concept that you can only explain using causal semantics. Gary Marcus recently, in his book Rebooting AI, comments that we need to stop building computer systems that merely get better and better at detecting statistical and start building computer systems that from moment of assembly innately grasp three basic concepts: time, space, and causality. And then
having problems with your audio getting choppy. Maybe you can turn the video off and that'll preserve some bandwidth.
How do I do that? Stop video. Okay. All right. And okay, you can still see my screen okay, right?
Yes.
Okay, and then so at NeurIPS also, Yashia Bengio gave a talk where he about it going from system 1 to system 2 level machines, and he has talks extensively about causality in that talk. And here's a quote from him on that talk where once a machine can understand the causal structure of the world and produce plans to take advantage of the fact that they are not passive in the environment and can be active and acquire knowledge, we will be getting to a better standard of application. So even the people who are deep learning luminaries are very focused on causality. We know causality is an issue that we need to address in our algorithms. I just want to, before going further, make it clear that I personally believe that there is a strong role of deep learning with causal modeling. I think to actually get to the more interesting models, we need to be integrating the two. We've also seen at recent conferences more causal inference publications, more workshops, more posters, more talks, more tutorials. Unless you've been living in a cave, you will have heard of the recent discussions about algorithmic bias and AI fairness. And part of the reason we're hearing a lot about causal reasoning is because it has a lot to do with these problems. So if you talk to a causal inference researcher, they'll tell you that the difference between discrimination and mere statistical bias is that difference needs to be explained in terms of, again, causal reasoning, causal semantics. I'm going to, here's an overview of what I hope to talk about. First, talking about what a causal model is and what it can do that deep learning can't. I think it's important to talk about what people in tech and big tech companies we see on the West Coast are doing with causality and how that integrates with whatever it is they're doing with machine learning. You can get started with causal inference and causal modeling without having to do things that are completely tangential to the skills that you already have. And finally, I'll talk about some tutorials that you can dive right into to get started. And we'll talk about this collaboration with This Week in ML. So starting off, the way to understand the difference between machine learning models that are causal and machine learning models that are not is that, you know, at a basic level, all machine learning is telling you about statistical association. In some cases, very high dimensional and nuanced statistical association, but nonetheless statistical association. So statistical association is saying, you know, given X, what is Y likely to be? You know, so the way you would say that in looking at, yeah, an exercise would say, given somebody on an exercise regime, what BMI are they likely to have? And so, you know, this is kind of why deep learning is so powerful, because it's, if you give it enough data, it can find these types of association relationships that are highly nonlinear and highly have a lot that are high dimensional and just would not be able to be detected using classical statistical methods. Now, the second we start becoming causal, we start talking about, at a basic level, interventions. And interventions say, if we were to force X to some value, how would that affect Y? So in this case, if in our BMI case, if we were to force someone to start an exercise regime, what will be the effect on BMI? That's different from having observed somebody. We're saying now we're going to force somebody to start an exercise regime. And this kind of breaks standard machine learning models, including deep learning, because will future data differ from the data that you trained your model on?
So you were talking about intervention, and there were some questions actually that came up already. Why can't deep learning do intervention? For example, couldn't you have a separate discriminator that checks if both pre and post intervention are in the data set?
I'm going to punt on that question. I have a slide that addresses that.
Okay.
But what I will say is that, like, if you, without what that person just suggested, if you just say trained a model using supervised learning, and then you're going to start applying interventions to the features and see what it had on your target variable, that wouldn't work. But deep learning can come up, has techniques in terms of training and loss functions that could help you find ways around that.
Okay.
What was the other question?
Oh, is intervention different from explainability?
Yes.
I.e., how do small changes in inputs change outputs?
Yes. So explainability, say for example, a linear regression model is not by definition a causal model, but you can explain what it's doing. You can explain, for example, what a change in the input does how it will affect the change in the output.
All right. Yeah. Now that we've demonstrated that your audio is solid, let's have you continue on the presentation, and we'll come back to the Q&A at the end.
Good. Finally, the kind of penultimate level of causal reasoning is counterfactual reasoning, which is phrased as in English using a kind of present past modal, which kind of grammar form. Say, given X and Y, what would Y have been if X had been different? So all else equal, for what would my BMI have been had I started that exercise regime a year ago, for example. And so this requires not only a representation of cause-effect relationships, but a way of simulating the proposed alternative outcome. In this case, what would Y have been had X been different, conditional on what you already observed. And so to kind of tie it to some kind of concrete computer vision examples, we can imagine that we had this data set of images of boxers, right? And we we know, for example, we can distinguish boxer from images of other sportsmen by, applying a label boxer, and then, our algorithm will find statistical associations between certain combinations of pixels and the label. And so if we sample from the set, we sample randomly from the set, we'll get, images of people training, of people getting bloodied in a fight, of people posing for, glamour shots. And we'll see things like, these will skew male, right? Because if you go on to Google Images and search boxing or boxer, you're going to see mostly images of men. Now, an intervention would say, okay, let me take my model and fix gender to female. Fix gender to female. Now, this is different from just filtering your samples based on gender, because if you did that, you would see different behavior of things not related to gender. So, for example, the backgrounds, the clothes being worn, for example, all of those things which are not well, maybe not clothes, but you would see variation in things that are not causally affected by gender, because that's what the association in the data says. You would say, for example, see more of a certain kind of background in the images of females than you would with the men. However, if you did an intervention, you expect the only thing to change is the gender and everything that is caused by gender downstream. So in this case, we would expect to see, if I did the intervention, the same sample distribution of images of women training, of women being bloodied in a fight, and of women posing for glamour shots. And then finally, the counterfactual means, the way that you would reason there is say, conditional on something you see, in this case, an image of a female boxer, how would that image be different if we change something about it? In this case, say, if you had a variable that you can interact with for the ethnicity of the subject of the picture. And so in this case, you would, conditioning on everything being the same, change only things that are caused downstream by some latent ethnicity variable. So of course, these are things that we have seen deep learning do, and we can do these with deep learning if we, in a kind of brute force way, where we use curated data sets, where we use special training procedures. So for example, deep fakes are essentially brute force counterfactual predictions. However, in order to accomplish this with deep learning, you'd have to plan your use cases for your model, the types of intervention and counterfactual questions that you want to answer in advance, and then spend a great deal of effort, perhaps expense, curating a data set that would allow you to solve specifically those issues. But a true causal model would be able to handle any use case you could throw at it. It would require less data to train. You would have less glitches like you see in some of these images on the right here, and its components that you trained on one data set, because they reflect some causal mechanism in nature, they should be transferable between data sets and domains. So going back to interventions, one of the reasons that interventions are critical in machine learning is because often in machine learning, we're using our algorithms to make decisions. So we can imagine a scenario where every morning we wake up, we take measurements from a barometer and predict whether or not it's going to rain that day. So we just do that for a while. We get a whole block of training data. And then we productionize our model and start predicting what the weather for the day after we wake up, and then use that to decide whether or not to carry the umbrella. And as we're doing that, we're still collecting more data about whether or not we were right or wrong. So in this case, in the morning, in the first case in training block 2, we predicted sun. We did not bring an umbrella. We were right. And in the second case, we predicted rain. We brought an umbrella. We were right. In the third case, there was rain. We did not bring predicted rain. We did not bring an umbrella, but we were wrong. There actually was sun that day. But that's fine, because we'll just take those those new examples and feed them back into our collective data set, and then retrain the model at a later date and get more accurate predictions. However, we can look at a similar scenario in, say, business, where we're looking at business analytics predictions, looking at business news, and predicting whether or not our business is going to make money this quarter or lose money this quarter. And then we collect that data for a while, we train a model, we productionize it, but then after we productionize it, we use the predictions to help us decide whether or not to run an ad. And we get the same kinds of mistakes and same types of errors, but also the same types of correct conclusions that we had before, exactly the same time. But what the problem is that the advertisements themselves they are affecting future revenue, right? That's the whole point of an advertisement, to make revenue go up later. But while in the rain case, the weather doesn't care whether or not we bring an umbrella. This kind of negative feedback issue happens a lot in, say, fraud detection, credits. So you hear, like, for example, credit card companies will productionize a model that predicts whether or not a transaction is fraudulent, but then but as they continue to collect training data, all of the fraud cases that end up in that data, all the things that are labeled as fraud, become only these weird edge cases of fraud that were able to evade the prediction of the initial algorithm. So now when you retrain your algorithm on that new fraud data, it'll be very biased towards these extreme cases. And then finally, it's a real interesting question. One that gets me most excited is, what elements of counterfactual reasoning, how are they useful in machine learning? What problems are we going to solve with these types of reasoning? And I would argue that the biggest impact that we're going to see here is in agents making decisions in uncertain environments. So these are bandits, Markov decision processes, reinforcement learning. What we want to do is reason about agents based on how they performed in production. So, for example, I have an agent making decisions about placement of ads on a website, and I say, based on these logs, had we given this agent a different ad placement policy, how much better would it have done? I might want to do that without actually running an A/B test, because running the A/B test will cost money. I want to just look at the data and just get a kind of preliminary answer to that question. But of course, we want to go further than that, and we actually want to have the agent reason counterfactually about its own actions. So to say, we want the agent to reason like this: I did what I thought was best given what I knew at the time, but given what I know now, having collected more data about my environment, I believe I would have gotten more reward had I done action A instead of action B. So I'm going to update my policy so that when I encounter a situation like that again, I'm not going to make the same mistake. This is called counterfactual regret optimization, and it's powering some of the best, game playing algorithms. Okay, so what are the big tech companies doing with causality? And so what we expect these companies, because we know that they're at the cutting edge of AI, to also be doing, if this causal inference thing is important, they ought to be doing something there as well. What are they doing? So what I found in kind of working in the industry and talking to colleagues who work in the industry is that there's actually little cross-pollination between people who work on implementing algorithms, machine learning algorithms, doing ML research at these companies, and people who are working on causal inference problems. And I'll explain why a little bit. But to do that, I have to kind of give you an idea of what a causal reasoning engine is. And if this can be something that you implement in code, it can be something that you just have as a kind of R script or something like that. But no matter how you implement it, you're doing something along these lines, where you start with a causal model with some assumptions about the cause and effect relationships between the variables and some parameters that parameterize the strengths of those interactions. And then you have some, you have an inference engine. So you're gonna say, okay, I have some data, I have some causal query that I want answered. The first thing I need to do is see if I can even answer this question given this data. That's called identifiability. And this is an element. This is an idea from stats, right? Then once I know I can identify it, I need to figure out what the S-demand is. That means I need to figure out what my recipe is for coming up with some statistic that will answer my query. And then finally, I have my estimator, and this is, so given my data, how do I estimate this statistic? And, all this, the usual considerations of, bias versus variance come into play there. But this is, when I teach this to people who are machine learning engineers, they tend to have questions about the identifiability part, because in machine learning, we as a culture are taught that the way around most problems is to get more data, to use more innovative architectures, to use clever loss functions, to use hacks in our training procedure. And but part of the issue with causal reasoning is that you kind of have to know from in terms of mathematical language, whether or not the thing that you're trying to estimate is even possible to estimate given your assumptions and your data. If you've seen causal inference, you probably know what a directed graph is. It's very straightforward to represent causality with a directed graph, where X is just the cause of Y, where the edge talks about where the edge source is the cause and the edge target is the effect. And so data scientists in industry are typically working on problems where they're trying to estimate something called a causal effect. So a causal effect is a quantification of the magnitude of impact a cause has on an effect. So usually this is quantified in terms of how much the effect changes given a change in the value of the cause. So while controlling for other variables that we call confounders. So when the cause has two levels, like as in treatment versus control, or as in A versus B in an A/B test, it's typically just the difference between the predicted values of the effect given both levels of the cause after controlling for confounders. So imagine now you're a data scientist at Netflix. Netflix, if you use Netflix, maybe a couple months ago you logged in and you saw a trailer for The Witcher, which is a video game, or which is a series based on a popular video game. When you go into that dashboard of Netflix, they're using experimentation to test and optimize your experience with basically everything you see there, including what trailers make it up to that top bar. So the experiments themselves are designed to estimate causal effects. So for this group of users, what is the effect of playing the Witcher trailer on you actually going on to view the Witcher series? And this is actually can be a challenging issue. So if, from a traditional stat standpoint, you might just say like, okay, randomly assign them to different groups. Random assignment is a kind of intervention that breaks confounding causes influence on the variable that you're interested in. But once you randomly assign something to somebody, some things that can happen that get in the way of estimating causal effects. So say, for example, after you see the trailer, that impacts whether or not you read an article about The Witcher. Similarly, whether, Netflix has no control about whether Witcher information is popping up in your social media feed. Both of those factors, and the fact that you might have some friends at work who are recommending The Witcher, just also impacts whether or not you read a review article. And then all of those factors, including the review article and having watched the trailer, impacts whether or not you actually go on to watch it. So what you're trying to do as a data scientist is separate out that blue area there, which is the causal effect that you're interested in, from all of those other sources of statistical association. And so what this means is that at these companies, people who are working on causal inference tend to be on these types of experimentation teams who are just constantly A/B testing or doing more sophisticated bandit-style tests on everything on the platform in order to optimize whatever KPI, whatever metric they're interested in. So if you look at job advertisements, for example, for this one for Facebook, this is an internship advertisement. Even in their R&D section, they're talking about marketing science. They're talking about measurement approaches and experimental approaches to enhance advertising through different marketing channels. Similarly, talking about Netflix again, here's a job applications online now. This is as closest to kind of machine learning as they get, where they have some machine learning recommendation algorithms, and they want people to run experiments on basically the hyperparameters of these algorithms. So so you treat those hyperparameters as the knob that you turn in the experiment, and then you want to figure out the causal inference of a parameter on the ultimate outcome, some kind of metric of performance for recommendation. So literally they mentioned causal inference approaches inside the responsibilities of this job post. I'll talk briefly about how the typical machine learning scientist or machine learning engineer can dive into causal modeling without having to go back to a graduate school in econometrics or epidemiology. So we mentioned this causal reasoning engine, and one thing you can do there for those assumptions is encode it as a directed acyclic graph. Most people, a lot of the people in the causal inference community stop there, but as a machine learning person, you can take that causal acyclic graph and implement it as a directed graphical model, right? And it turns out that because these models can be used to represent the assumption that something is a cause and something's an effect, you can treat some of the graphical models that we use or in machine learning, some of the latent variable models. I'm talking about things you've heard of before, like mixture models, mixed membership models, Gaussian mixture models, for example, matrix factorization models like you might use for recommendation, hidden Markov models that you might use for time series data, and you can treat these as causal models. You can apply intervention to them and predict the effect of the intervention. So in this case, for example, your structural causal variables here in this mixture model, this is a plate notation image of a mixture model. Z and X are your structural variables. These are things that you reason about in terms about cause. Z is a cause of X, and all of the Greek letters here are just parameters for the conditional probability distributions of these structural variables. And so in this case, the kind of causal story is that Z is a switch that helps X, that changes the mean value of X. So Z is like a light switch, and X is the light in this case. Now, if we think about how we can iteratively build some of these kind of directed graphical models, this is the kind of build, compute, critique, repeat framework introduced by David Bly. This step here where you criticize the model, where what that means is that you evaluate the model in terms of cross-validation, how well it fits a data set, how well it predicts unseen data. In his framework, you build the model by constantly looking at how well it performs on some test data, and then making changes to the model that will enhance its performance. But since we have one thing you can do with a causal model is you can use intervention-based critique. So Karl Popper, the philosopher of science, he argues that he is very down on trying to prove a hypothesis by evidence, right? In machine learning terms, he doesn't like the idea that you would try to say one model is better than another simply by how well it fits some data, how well it predicts some data. He says the only real thing you can rely on, at least from a scientific standpoint, is the ability to refute the model if it's false, which you can do with a causal model, because a causal model will predict the outcome of an intervention. So if you, for example, use your causal model to predict whether or not an ad campaign will succeed, and the ad campaign doesn't succeed, your model is wrong and you need to improve it. And this type of model iteration, where you falsify your model and then rebuild it and then keep going until you can't falsify it anymore, and then perhaps then trying to make tweaks to the model that make it more optimal towards observed data. This is the same type of model iteration technique that George Soros uses when he's coming up with models for currency trading. He says, you know, I'm only rich because I know when I'm wrong, and I basically survive by recognizing my mistakes. So this causal modeling, one thing I teach the people that I work with is say, hey, you need to be very laissez-faire when it comes to your models. You want to reject them and then come up with better ones that work across various data sets and do the things that you expect it to do. How are we doing on time?
Yeah, we've got 10 minutes, so it might be prudent to kind of transition into talking about the course details, because I'm sure there'll be a question about that. Not necessarily right now, but you know, when there's a good transition point.
Okay. So the only thing I was going to say now is that I've introduced to you these types of models you see in machine learning, latent variable models, which include things like variational autoencoders. This is where deep nets can really be brought to bear on these types of problems, where you can have, say, for example, multivariate variables that are causes and that are effect, and there's a nonlinear relationship between the cause and the parameters of the effect. Another way to bring in way this is having an impact on machine learning is that part of the trick was what in causality, you know, oftentimes in machine learning we're working with data sets where we have, say, a very low level feature like pixels or words, tokens in natural language, and it doesn't really make sense to say like one pixel affects another pixel. It doesn't make sense to say that one word causes the other word in the sentence. But there is a technique in deep learning called analysis by synthesis, where we develop a kind of grammar of high level concepts and then use that to generate through a forward network an image. We use a training procedure to make a training procedure to make the generation of those low level features look a lot like real data, but given some real data, we can now kind of go and get some kind of high level hierarchy representation of the core concepts in that data point, and that kind of those kinds of high level concepts, we can define those in terms of a causal grammar. And so so in other words, you can use causality to reason at a high level about high level abstractions underlying things that latent ideas that generate a low level features like pixels and words. Best libraries to get started. I'll share, just to be brief on this, I'll share a link with you to tutorials for the causal modeling course that are all online in a Git repo. You don't have to sign up for the course to get access to these. They'll be, of course, disconnected from the broader content, but if you don't have the time or the budget to go into the course, then you can, these are a great place to get started. And that's all available for you on the course repo. Okay, so talking a little bit about the workshop, I'm introducing two courses, a shorter one and a longer one, and the longer one includes the shorter one. And the first one is called Refactored Thinking for Machine Learning. So if you go through this TWIML AI link to the Causality course thing, the page, you will see the set of courses being offered, but these are all individual modules here inside these two online workshops. So that's this first one here is refactored thinking for machine learning and causality. It includes 2 of these modules here, one called model-based thinking and machine learning, the second one called do causality like a Bayesian. This causal modeling and machine learning track includes all 6 of these modules. And I think I'm going to, rather than explain too much about this, I'll leave that to the Q&A. But I'll say, that this is the nature of the workshop that we're doing with this week in machine learning. So it's 20% off any of the options for buying these courses. So like this gives you unlimited access to the online course material. So this is in perpetuity. You get engagement with me and the other instructors through Slack. You can make one-on-one appointments with the instructor throughout the duration of the course. So the duration of the short course is 1 month. For the long course, it's 4 months. Every Saturday with Sam, we're doing a webinar on the course material covered that week. And then finally, so there's assignments and projects that you can do with this course, and they will be evaluated by human graders. And then finally, you get access to an active course forum where you can, where's the forum? Here it is. So where you can get answered questions about the, say, tutorials and the assignments and just general information about, or follow-up questions about the lecture. Here is, if you go to Robert Ness /Causal ML, there's a tutorials folder here, and that's where you can find all of the, these are Python notebooks and also R Markdown notebooks, showing you some very useful walkthroughs for how to work the some of the code for these models. But these are all covered in depth in the course, and we and if you sign up for the course, of course, we'll give you feedback on and answer your questions when trying to implement some of these models. This is kind of this is what the course looks like on the inside. So this first module here, model-based thinking and machine learning, covers 3 sections here, and kind of an introduction to the philosophy behind this model-based machine learning approach and how it relates to causality, an introduction to modeling with directed models, causal modeling with directed models, and then introduction to building causal models using a machine learning technique called probabilistic programming. So you get access to all these materials, and then you have access to them after the course ends. So you can look and go through all the materials here. If there are the price for the short course is $299, 20% off for this week in machine learning, and for the full course it's $1,200. But you can do 4 monthly. You can do 4 payments of $320. Again, 20% off of both of those prices. There's a 30-day money-back guarantee. And if you decide just to do the refactored thinking for machine learning and causality now, and then want to continue with the actual, with the remainder of the courses upon finishing this, you'll still be able to apply your coupon code to opt into those courses as well. Okay, that's what I got. Questions?
And did you mention the duration of the various courses?
Yeah, so for the long form course, it's 4 months, starting from when the student signs up, and for the short course, it's 1 month.
Got it. And so starting from when a student signs up, meaning the student can sign up at any time and do it self-paced, but the study group is going to start next week, Saturday, and that's going to run for the at least for the first course, did you say 4 weeks? And then continue on for folks doing the full course. Is that right?
Yeah, that's right. And to say that, like, these aren't courses you can sign up for any time. I open enrollment for them just because I stay actively engaged with students throughout the whole process. So just to stay sane, I just have enrollment periods. So I'm opening enrollment for this week in ML. But once everybody, once that enrollment period is done, and I leave that kind of up to you in terms of when the course starts, I'll close enrollment. So, and then won't open it up until I have bandwidth to deal with the new cohort.
Cool. So we've been getting some questions in, and I will go through these. The first from Tom is, are the study groups recorded in the event we can't attend in person? The answer to that is yes. This session and the following sessions will be recorded. Hyam asked, will these slides be made available? Can you make these slides available to the group, Robert?
Yeah, no problem.
Oh, cool. Your video's back on.
No.
Looks like you're on another phone call. Jess asks about the overlap between the two. If we take the short course first, then want to continue into the longer course, how much overlap is there between the two? And are we paying full price for both, but with the 20% discount? So you said if you take, so first of all, I can answer this question, a part of it at least. The long course includes the short course, at least the way they're bundled on the site. There are 6 underlying modules. The first 2 modules are the short course, and all 6 modules are the long course. And Robert, you said that when you join, if you do the short course and you want to do the long course, you can apply the coupon for the long course. I think for most people listening, that suggests the 20% discount, but I think in our previous conversations, you were saying you can also get a credit for the short course, so you're not like double paying.
No, yeah. No, I won't. You won't pay, for example, like full price for all of them and then pay for the first 2 courses. Again, that's not how it'll work. Right. What I'll do is I'll bundle the remaining courses, or depending on what students want, say like, hey, I've done this, I kind of know it. I don't really care about the counterfactual stuff. I just want to learn the causal kind of inference and practice stuff. So I'll package them appropriately to the group. But no, I don't plan to fleece anybody.
And so Sunny asks, how is the 20% discount applied? That is applied by using that TWIMLAI.com/causality course link. How much time should we expect to spend per week to complete the course? Stefan asks, for a rookie.
This course is...
And while you're at that, what are your expectations in terms of prior experiences, technical knowledge, et cetera, coding knowledge?
Great question.
In order to take the course?
Okay, so I'll say this, that this course is designed for engineers who have, number one, full-time jobs and commitments, and who have, say, different levels of interest for how deep they want to go. So with this refactoring course, for example, there's very little math in it. There are some tutorials that you can play with, but I assume that I designed it so that if you say like, listen, I just kind of want to read the lectures, go through the videos, and leave it at that, and then just kind of know at a high level what kind of have a mental model for how everything fits together, and then be able to dive deeper, should I want to do that later for one reason or another. Or if you, especially when we get into the material on causal identification estimation, which is more along the lines of the Netflix, Facebook stuff. There we'll introduce some math, but the math is always discrete kind of probability. So it's like, joint probability, conditional probability, Bayes rule, that kind of stuff. And so there are some technical concepts introduced there, but in terms of actually reasoning through them, just having exposure to things like conditional probability, what does conditional independence mean? That's sufficient. In practice, these methods can get pretty hairy in terms of the math, but that all has to do with just like a specific, estimation problem. But we're not going to dive into any of that. We're just looking at like, what is the problem? How do we solve it? And then what are the methods out there for solving it? And then if you wanted to go deep on those methods, you can do that. So the course, basically a little bit of background on kind of stats and probability, but and some familiarity with and you have to be comfortable coding a little bit, or else the tutorials aren't going to be particularly useful for you.
Question from Jess with regards to the timing. If we proceed now with the short course, then want to do the long course after, will it be a seamless transition into continuing with regard to the mentoring and study group? Are you doing the TWIML study group through the entire course sequence? I think is the question there. And as a secondary question, are the applied projects that you mentioned, are those all on your own, or will those be instructor led or study group led in some way?
So for the first part of the question, as far as the ability to kind of like engage through the study group and through, say for example, I think just the study group, right? That'll be seamless. The only thing that kind of has to be done if you decide to continue is that I have to enroll you into other courses on the platform. And then that's straightforward. If I can do that for a student, or they can do it themselves once I open up enrollment for it. In terms of the tutorials and the project tutorials, I'm very happy. Like there's most of the tutorials are kind of like very basic. They walk you through the core ideas, and then there are a few tutorials that are proper projects, right? So there's one on causal variational inference. There's one on causal variational autoencoders. There's one on a implementation of a technique for predicting whether or not adding an actor to a movie would increase revenue, box office revenue. It's using some sophisticated latent variable modeling techniques in PyTorch. Those I'm happy to do an individual walkthrough on a one-by-one basis, or through the webinar if there's interest in that. Some people have projects. Some people have interest in some projects. Some people have interest in others.
All right, cool. Blair asks, you mentioned ads as an example. Will ads feature prominently in the course? And, kind of by extension, what kind of practical stuff can participants expect to be exposed to?
If you go into the literature on causal inference, you'll see a lot of examples from epidemiology, from public health, from a little bit of econometrics. And one of the unique things about this course offering is that they are related to problems that you see in machine learning and or tech. Ad examples feature prominently because it's simple to do. It's simple to just say like, we want to, or like say a feature or something like that. I want to introduce a new feature to a platform, for example. It's easy to explain, and without the model getting too overly complex such that you can't really teach the core idea. So to put it shortly, I want all of the examples in this course to be the types of examples that people would see in machine learning and tech in general. That said, I think if you're here because you want to, go do some public health stuff, you'll definitely find the math and the explanations just the same as you would find anywhere else.
Another question about the programming environments that you use, PyTorch or TensorFlow based?
So there's a little bit of, so first I want to say there's a little bit of R, so R for representing of causal Bayesian networks, just because there's a package called bnlearn, which typically is the best. There's no other package that really kind of surpasses it for that problem. Although I do have links and references to comparable packages in Python, such as pgmpy, for example. Most of the examples are using Pyro, which is a probabilistic modeling extension on PyTorch, we're using that because some of the core abstractions that we need to work with in causal inference, for example, interventions, there isn't another tensor-based computational graph framework that has these abstractions implemented. Pyro is supported by the Uber AI team, and I'm very much in connection with them, and whenever they update something. So recently I was working with them on having them on some abstractions that are specific to causal inference. So it really is the best tensor-based framework out there for incorporating causality into models.
Tom is looking for some additional detail on the syllabus.
Sure. Share my screen again. So Tom, I don't know if you're able to visit the site. If you click on either of the workshop options, these individual classes here, you click on any one of them, they'll have some explanations for what is expected in the course. The model-based machine learning course, this is kind of what the syllabus looks like on the inside. But I have, Sam was yelling at me the other day for doing this. But if you go to my GitHub account, Causal ML, there's an academic syllabus here that maps fairly well to these online workshops. So if you go to syllabus.md here, you can't see my screen. I'm sharing the wrong screen. There you go. So Causal ML, and so a more detailed kind of breakdown of what's in every course is here. We're gradually kind of updating this and moving it towards the platform. But this if you really want to go deep into what to expect, this is a good place to see what's going to be in there. But in terms of just the topics covered, most of this is also on the website. So this is going to the same place where you find the tutorials. There's a link here called Syllabus, or markdown file called Syllabus, and again, this syllabus is oriented towards some graduate students at Northeastern, but you'll find the online platform at All Deep and this particular syllabus are not going to deviate very much.
Cool. Ellen is asking if you know Bayesian modeling already, will you get much out of this course? How much overlap is there?
Well, that's a good question. So when someone says Bayesian modeling, so do you mean? I'm not sure if I can see the comments. Does that person mean just kind of understanding Bayes' rule and kind of like how a naive Bayesian classifier works, or does that person like do probabilistic modeling? I would say that
a course on Bayesian modeling.
Yeah, so there is there's a course that's covering Bayesianism and model building. Let's see here.
And why don't you reach out to Robert on Slack and point him to that course, and he can clarify that.
So just to kind of to summarize though, if you should understand kind of what the cores of Bayes' rule is. If you don't have a background in probabilistic modeling, you will get one from this course. And if you do have a background in probabilistic modeling, you'll get a lot out of this course. But on top of that, you'll also understand kind of how to connect Bayesian reasoning, the kind of philosophy of Bayesian machine learning to causal modeling in this course, which is different from just kind of fitting latent variable models with Bayesian inference.
Cool. All right, it is a quarter after. We think we got most of the questions answered. Last one from Jess. I think if you use that link, it should automatically apply the coupon. If not, we can address that via Slack or something to make sure that
and
getting that.
Please feel free to reach out to me on Slack. I'm on the Slack channel. I'm responsive on Slack. We're all conditioned to be responsive on Slack these days. So.
And is the enrollment currently open in the course, or is that something a switch that you have to flip?
If you see the prices under a course, then it's open. So yes. So for the refactored thinking for machine learning, that's the short course, and for the long course, yes. Okay,
cool. All right. So again, if you use that link, you should. I clicked the link from TWIML and it said no. Well, we will follow up on that and make sure that it all works. And I think if you don't, if you get to a checkout screen and there's like a coupon code, it said no enrollment not open.
For which one?
For which one? So let's open up the TWIML AI /causality course.
You have to scroll to the bottom to see the open courses.
So if you scroll to the bottom, so
it says under workshop options.
Got it. There's a button at the top that says get notified when enrollment opens. But if you go all the way down to workshop options, you'll see the 2-course bundle. That's the short course that we've been referring to, and the 6-course bundle that is the long course that we've been referring to. Cool. We're on the same page. So again, now we're coming up on 20 after. I don't want to keep folks on this wonderful Saturday morning, but I am definitely appreciative of everyone for joining us. And thanks, Robert, so much for the great and informative presentation and for the course and for doing this with us. I'm really looking forward to this.
Thank you, Sam, and thanks everybody for joining. Sorry for the technical issues.
All right, everyone.